So while we're waiting for people to join, I can share a little bit my experience. I played a lot this week with optimizing performance of different things. And so one of the things I tried to get things to run under Octave. And in my experience, Octave is roughly 100 times slower than the same test. So it's not like 3 or 5 or 10. So I kind of played around with trying to come up with a high performance collection classes like balanced trees and whatever. And if I do it on the MATLAB, I'm getting comparable to the built-in classes. So it's hard to beat the built-ins, but it's close. We get in into the range of few milliseconds per operation, like lookup in the big collection or whatever. And on Octave, so it's we go basically from microseconds on MATLAB to milliseconds sometimes, or at least hundreds of microseconds on Octave, and it's really like I don't know. So it's interesting. Like now I understand better why MATLAB charges money. uh, but it's still a lot what they charge.
What's the operation that's slow just in general or specific?
It's like it looks like everything is very slow, but what was killingly slow was exceptions. So now in some places in the code we had like try catch uh, clauses, and this code is certainly way slower on Octave. But also the collection, basically what happens, we use map object to hold the blocks or to map blocks to the indices and backwards. And the Octave's implementation of map basically wraps a struct, and that would be okay because structures is extremely well performing also on Octave for small structs, but they have in contrast to MATLAB, which have a very flat response with the size, uh, Octave performance of the map goes down, and after 1,000 or so of entries, it just basically breaks together and falls apart. So, it's certainly a quadratic time penalty, or probably even worse than that. So it's basically not working for any large sequences. Okay, I think we are already a pretty decent crowd.
Yeah, maybe I can share well, I'm gonna make you host before I share because my sharing is a little flaky. So let's see. If I disappear, it's a bargain. I'll be back in a
Oh,
minute. Still see me?
yes.
All right, good. Um, yep, so a few items to go through before we let Jürgen take it away. Uh, Meeting date for next month. So I shouldn't be showing that. Let's see. So May 1st is a holiday, and then week after is ISMR. I'm sure everyone is traveling that Friday. So either we do it um, early that week. Let's see. That's clear. Okay.
Yeah, so basically we have May 1st, which is a bank holiday in many countries, in Europe at least. Or pre-SMRM Friday will already be in Cape Town and probably somewhere not in the office or not online. So I'm
Yeah.
pretty sure it's probably a little bit similar to many.
Yeah.
Even the 16th may not work because people might be traveling back from Iceland.
16th also similar, like I'm pretty sure many
Yeah.
people will be traveling back. So it feels to me
I-
that May is doomed, basically.
Yeah, maybe
Yes.
skip May and go for June.
Yeah.
Okay.
That sounds. I'm sure everyone would also be pretty tired. So
Yeah.
probably
5th
June
of
5th if
June.
there are no.
Yeah, 5th of June would be good.
Okay.
If that's not a holiday in Europe, then maybe we should go.
Well,
We'll just have to
you
check.
will laugh, but maybe it is. Let me check.
Yeah. No,
In in
I feel like I keep hearing about bank holidays all the time.
in Germany, there is this Pentecost and things somewhere around that time, which I always forget when they are because I'm not. So it's a school break, but not a holiday, as far as I can see. So I think we keep it there.
Right. And then we have, as always, if you want to share anything, we'd love to hear from you. You can volunteer to present. So June 5th would be the next one. If not, we will be proactive and hunt you down. So, but it's great if you can, if you have something to share that you think is ready, we'd love to hear it.
Yeah, I think best is basically if everybody's from the attendees experience this feeling that they need to say something to the rest of the group in roughly 2 months. Please just speak up or write something to the chat or write us thereafter. Okay.
Let's go on to the next one. Anything to mention there?
Yes. So basically, we think we have fixed the table undocked problem. At least we didn't see it anymore in our lab after we did the patch, and then I released. This is a new version on 31st of March, and also didn't hear back that somebody would still experience table undocked. So either people didn't try it out or it actually works. So, question to everybody: is it? Have you heard of something not working since the last update, or did you try the last update?
Um, can you guys hear me?
Yes.
Sorry, my camera is not working. I've tried the new patch, on the version 1.5.2. And I tried the table docking thing. So before the fix, there was a leftover table value, but after the fix, the table position is perfect. So I think that part is good. But I noticed another like a very subtle issue with the folder in with importing a sequence from the folder within the build-in. So and when you manually copy or copy the sequence to the my cockpit and then move the sequence back to the workplace again, And if that sequence is not in the base folder, but rather in a personal folder, there will be a pop-up error saying there's a parameter change. And then if you double click the sequence again to edit the path of the file, it'll lock up that drop down menu and trigger a restart workplace error. So
Okay. So interesting. So these do you save? So basically the workflow, you run the sequence, you have it in the execution queue, and then you copy it over to the exam explorer.
Yes.
And drag it back, basically.
Yes.
Okay, interesting. We'll check that.
Sure.
we
Yeah, because it's
we
kind of reproducible on my end for whatever sequence saved inside the personal folder.
okay, interesting.
Mm.
So we changed. We added some code basically in the new, not in this release, but in the February release we released.
I've noticed that in 151 and also this release, but yeah, well, for 142, since you have to import sequence from base folder, so there's no problem with it.
Okay. Yeah, so we changed the logic how the things are searched in the subfolders. So we'll double check that. Okay.
Yes,
Thanks.
sounds great. Thank you so much.
Good. Okay. Any other comments or experiences?
I have a question I can ask about, this is kind of CMAS specific.
Yeah.
The thing is, so I'm trying to understand the gradient limits that we need to use or we should be using when designing readout trajectories. So it seems that CMAS never uses the absolute max gradient, but they just use the max gradient amplitude, which is usually much lower than what the scanner can actually do.
Yes.
Is that what we should be respecting, or should we like use whatever is possible while being, PNS and forbidden frequency constraint? I'm trying to understand that.
Yeah, the logic. So this is the Siemens have this maximum gradient amplitude, nominal and absolute, and whatever they have like 4 or 5 types of maximum gradient amplitudes. Also, some of them are fixed, and some of them are dependent on whether you are now in the normal mode or quiet mode or high performance mode. So there's also like if you program in the idea sequences, maximum gradient property is extremely intransparent. It's very opaque in the way how it behaves. In the good old times when the cooling of the gradient hasn't been a problem, the general rule was that this maximum nominal gradient strength was the actual highest gradient strength divided by the square root of 3. That basically would be something that, imagine you think you're creating a sequence which uses intense gradients, and it happens so that at some point in your sequence you will create a combination of, so basically we'll play out maximum, in your definition, maximum gradient on all 3 axes. So that would be a linear. So the actual gradient played out at this moment would be a vector addition of this 3. So basically a diagonal of the cube in the parametric space of your gradient. And then if you play out such gradient and rotate this sequence once again by a golden angle, so that you will align this gradient actually with one of the physical axes, then limiting yourself preemptively to this 1 over square root of the maximum gradient would guarantee that your sequence is basically freely rotatable. And because the Siemens framework doesn't recheck the sequence after you reorient it, it's also true for IDEA. That's basically is a kind of a design requirement from Siemens to make sure that you never use a maximum gradient unless you know what you're doing. And if you want to know what you're doing, you have to use your own rotation matrices inside. So it's kind of getting a longer story, but it's a bit similar with Pulseq. If you know what you're doing, you can use the system maximum. If you don't want to be dependent on the orientation or either things, you have to derate your maximum gradient to be on the safe side. It's interesting though that the slew rate, so similar thinking should also be applied to the maximum slew rate, because if you ramp several gradients at the same time, your actual slew rate goes higher. Then now, if you rotate your gradient, you will actually be slewing on one channel. But I haven't seen the slew rate limits, which would be derated in the Siemens code anywhere. Now going very much back, so there's this difference between nominal and maximum gradient amplitude was previously like in the good old time set, where it was just a square root of 3.
Mhm.
But in the meantime, they derated further by the thermal model of the gradient. So basically, if you use the system specified maximum gradient, maximum nominal gradient, then the gradients are unlikely to overload your system. Your sequences are likely to run without temperature warnings and alike. And if you go above this nominal gradient, then it's possible that you will demand too much from your gradients. But again, typically the system is protected on different levels and you're not in danger of actually destroying it.
So on the CIMA, the absolute is like 191, which is good. And then the gradient max you can do is like 37 or something, which is like, 4 times lower than advertised. And that's what CIMA uses for like EPI or spirals.
Yes.
And interestingly, nominal is greater than this 37, which doesn't make much sense to me. And I'm kind
Yeah.
of
So there is another. So in terms of the readout, there is another limitation, which is related to your bandwidth, the receiver bandwidth. So if you use too high gradients, you will create a frequency dispersion over the field of view, which you will not be able to receive. So your Nyquist frequency limits for the gradients above roughly 40 millitesla per meter will limit your field of view basically. So you cannot use very, very high gradient strengths for the readout, because you will have basically the cutoff of the analog filter will already kill your signal at the periphery of the field of view, and then the analog filter will induce the phase reps. You will have the modulation of the intensity, which is due to the Q factor, so the resonance property of your receiver coils, because again, it's typically not extremely high. It's high, but not instantly high. So basically, if you're going into very, very high readout gradients, you have to handle a number of problems. So you need to be aware of those problems at least.
The
And
safe thing to do is to like not exceed. I see.
Well, but that's on the ADC side. So basically, on the ADC, there's also I noticed it's getting very, very tricky to use the ADC dwell times below 2 microseconds. It's possible, but tricky. So not all combinations then are possible. My feeling is that well above 2 microseconds, the system allows you pretty much everything which is divisible by 100 nanoseconds in terms of a dwell time, and also pretty much any number of samples if it's divisible by 4. But for faster sampling, strange limitations start to apply, which I don't completely understand. You sometimes need to try things out. So you can certainly use 1 microsecond, but things get tricky. And also around, so 1.6 microseconds I used one, but it's somehow tricky sometimes.
Thank you.
Okay, I think we need to make sure that we don't delay the start of Jürgen's presentation, so maybe we need to move on. But
sounds good. I can just spend a minute. Just need to spend 1 minute. I was just going to say what you just discussed. I think that aligns pretty well with what's going on in GE. So that most scanners, the minimum dwell time is actually 2 microseconds, and probably for the same underlying reasons that you just described, I'm guessing, which is interesting, except on the head gradient system where I believe they can do 1 microsecond. But it seems like, yeah, we should probably limit our dwell times to 2 microseconds or greater. That sounds like a good practice. I just wanted to briefly stay. I haven't really had time to really put anything together here, but the main thing I'm working on now, and if anyone wants to help test, and I found out yesterday as I was working with the MRF guys to debug, is that I'm trying out a scanner workflow that performs the MATLAB steps on the scanner using the MATLAB runtime that's installed on GE scanners. And so that will allow you to put the Pulseq file on the scanner, essentially install it using just one script, and then adjust the field of view also. So we've tested the field of view piece of this. So yeah, sorry again for the many websites here, but this is probably for those of you using GE, this is an example that you're probably familiar with, a 2D gradient echo example. So if you go to the parent folder, there's a general description here. And there's a link to this page. So this is new. So this is how you can prescribe the field of view on the console. So the idea here is to prescribe in the usual way on the console. And then there's a built-in command that GE provides that will get the prescription information, like the field of view, offset, and things like that. And you can dump that to a text file that you then process. And the idea is that this script here will take an intermediate sequence representation that's actually in a mat file, and they will write the PG file for you and the entry files as well. So this is set up, I don't have to go in detail, but it's basically set up with, you can create a list, essentially a protocol of any number of Pulseq sequences that belongs in your protocol. And once you've created that and you've set up your folder with some of these tools that this web page describes, in one line you can apply that field of view shift to that list of scans. So that way you can, once you have the mat files installed and separately, that sort of serves as the installation, and that will be there forever. And then during the scan, you can update the field of view and write the PG file interactively in this way. And the thing I'm looking at now is we actually had a case yesterday where there was a wrong sign in the frequency offset, so we're looking at that, but the workflow works. And so my next plan is to, and this is kind of related to Birkin's questions too, is to make the entire workflow just happen on the scanner, and that way we can get the gradient limits and the slew limits directly from the config file, so that you don't have to look them up yourself. And that also makes things safer, so that you just have to deal with the Pulseq file, and the MATLAB runtime on the scanner will take care of the rest. So that's the next piece I'm going to work on. But this field of view step, it does work. If you do something and you find that it's not producing the right shift, let me know, and we can maybe look at it. But that's the update on that. So yeah, so check it out or let me know. We can also, I can demo this on Zoom anytime with any of these. So just let me know. Okay. I think we're good. So yeah, we're really excited to have you here, Jürgen. So the floor is yours. Stop sharing.
Okay. I'll try to share.
Yes, it's coming.
Okay. Okay, you should see it now. Okay, so I would like to give you a brief introduction into what I have been doing on and on the TSE sequence, which was actually the sequence I started with when I got into Pulseq in the very ancient old times. I remember when I first started, what the gradients had to be ramped down to 0 at the end of each block. So Maxime did a lot of development to make that happen. But it also means that in the sequence code you find a lot of old junk. If I had to redo it today, I would probably do a much better job, but I'm strictly addicted of as long as it works, don't fix it school of software engineering. So I actually find it quite appropriate to do that today, because I noted that nearly to the day it's the 40th birthday of the original rare paper. I mean, that has been intensely used. I don't need to tell that to anybody. So you may ask, after 40 years, is there still something interesting with respect to the sequence? All the sequence code is already available on GitHub. If you look into the repository, you will actually see two sequences, TSE Plus and TSE Fast, and I'll get into that pretty soon. So the basic sequence structure, I've put up the sequence generation file such that all the relevant parameters are stored in two structures, ACQP and ACQ, where the ACQP are the parameters which you normally expect to be able to modify on the GUI of your scanner, so field of view and whatever the standard parameters are, whereas the ACQ parameters are more the ones for the internal workings relating to the duration of pulses, amplitudes of spoilers, and so on. And the sequence parameters are automatically stored at the end of the sequence creation in a mat file, so that you later on you know what you have been doing. If you look at the sequence code, you see that there's a loop wrapped around the whole sequence, the KSEC loop, and that allows you to generate multiple sequences in one run of the sequence. Whenever nsec is greater than 1, then a parameter file, my tsepar.m, is called, and in that parameter file you can specify whatever parameters you want to modify. That can be very simple, like just a vector containing different effective echo times, and it can be very complicated. You can basically modify whatever parameter you like. And I like to use that whenever I set up, whenever I plan a session, I just create all the sequences I want to run in one go, and then I have good control and good memory of what the individual sequences represent. Coming to the difference of this ominous TSE Plus versus TSE Fast, actually, I would say 98% of the code is identical. The difference arises in the way the parameters, the sequence is implemented. The TSE Plus takes the conventional approach, so you have an RF pulse, and then you have a time for phase encoding and for spoiling, and then you have a readout time, and then you have the phase encode rewinder and the spoiler, and so on. Whereas in the TSE Fast, the gradients can be made to overlap. And that allows you to quite considerably shorten the echo spacing while keeping the readout time the same, as you see here at the bottom. So sequence echo spacing has been just mildly reduced from 4 to 3.2 milliseconds. And since the readout gradient and phase encoding gradient overlap, then you get for high phase encoding gradients, you get this rounding of the edges of the actual K-space covered. But yeah, cutting off these edges really doesn't affect the imaging behavior at all. So you see here on the top the image with a somewhat longer echo spacing, on the bottom with a shorter echo spacing. The images look nearly identical. One could say that the image at the bottom looks somewhat slightly sharper because of the shorter overall echo train decay. Apart from that, sequences are nearly 100% identical. One change I made is that whereas for the TSE plus sequence, you have to adapt the readout time to your readout matrix to fit the ADC raster time, whereas for the TSE fast, you can be free in your choice. You just do oversampling whenever your matrix size doesn't fit to the acquisition window. How is that implemented? I mean, if you let the gradients overlap, then the typical block structure doesn't really work anymore. So in the TSE plus, you have the refocusing pulse, you have the phase encoding and spoiler, you have the readout and the phase encoding rewind. In the TSE plus, all the gradients along the three axes are combined using that fabulous function add gradients, and then the whole echo spacing is just one block. So you put everything into one block. I'm not sure whether that's the intended use of add gradients, but it does work and it makes life very, very easy and gets you to the end. So what are the different modifications I have been working with? Well, I implemented all the standard modes, so you can have variable flip angle schemes, different phase encoding schemes. I'm coming to that, half Fourier Grappa sense, and so on. And I will not talk much about these. I will more focus on describing some of the special modes I have been working on and off over the last three or four years. Let's start with the variable flip angles. I don't want to go into that in detail. On the top left, you see the flip angle pattern, which I like to use. So you choose your target flip angle, 120 degree, you ramp down slowly in order to maximize your signal intensity. And after you acquired the K-space 0 point, you ramp down the flip angle. And this way, you end up with only 35% of the RF power required for 180 degree throughout. And if you compare the signal intensities you see for the relevant tissues, gray matter, white matter, the signal intensity is more or less identical. You lose something with CSF, which is actually an advantage because you don't want the appearance of the image to be too much dominated by CSF. And that's quite considerably better than if you use a constant 120 degree, which is used quite often, which leads to signal modulations and also lets you lose some signal. There's many different flip angle schemes implemented. You have to look in the manual to see what that's all about, and you're free to play with your own flip angle schemes. Phase encoding modes, I also tried to be rather comprehensive there. I have to say, whenever I worked with the sequence over the last decades, I normally always use the linear phase encoding scheme because it's very simple to implement and it gives you good results. There has been the phase encoding scheme introduced by Philip Melke already long time ago, more than 30 years ago, which is kind of a centric scheme. So if you go full centric, you would go from 0 in both directions in alternating steps in order to achieve a given 0 point for the readout of your effective echo time. You have to shift that, and in the phase and centric mode, the shift is done basically in the vertical direction, so in the phase encoding direction. But one could also imagine to make the shift of the centric encoding scheme along the readout axis. So that's basically the options you have. It starts to look quite different if you have an odd number of echo trains into which you distribute the phase encoding. So for linear, everything is the same, just one more echo train. For phase, you see you have then 2 echo trains with this steeper ramp and a jump in the middle, and one with a little bit slower ramp. For centric, you really alternate, because if you sample every 3rd point, you jump from one branch of this wedge to the other, and the same for the centric S. There's also a quite often used implementation with a single shot echo train and half Fourier reconstruction. This is not really favorable with the linear phase encoding. If you really want to put the phase encoding 0 into the first echo, that would mean that the second half of your reference data for your POX reconstruction goes to the end of the echo train, which will not give you good results, whereas that really leads to the same trajectory for phase centric and centric S, in which you first acquire your reference scans going to and fro, and then you go up in one scale. You have very different looking phase encoding trajectories. So this is an implementation where you really see big differences in the actual way the K-space is sampled. If you look at images produced with that, you see the images, they are really identical. That's more an educational gimmick I built in there. It doesn't have really practical consequences beyond that implementation with a single shot where you like to use the centric approach. So let's come to some of the special modes, and the first one I'd like to discuss is weighted averaging. This is actually something which has been published by Markus von Kienlin for phosphorus chemical shift imaging, where you are plagued with very low signal to noise. I wanted to implement that a long time on the IDEA environment for high resolution 3D space. We had a very nice 3D space sequence with a 0.65 millimeter isotropic resolution, which gave good results. We wanted to get 0.5, but we never got a decent signal to noise for 0.5. So I thought weighted averaging could do it, but in the IDEA environment, there is just no way to make averages with a different number of samples per average. So eventually we gave that up. If you do it just this way and then combine the data and reconstruct, you get a heavy weighting of the center of K-space, meaning a blurring of your images. You can reduce the blurring by appropriate weighting of the averages according to the number of samples per K-space sample, and this way you can normalize the noise. Implementation with TSE is a bit tricky because you have to then redistribute to the various averages into your echo trains. If you just concatenate your scans, you see you end up with different weighting of adjacent K-space samples, which might give you some artifacts. So what I did is I just resorted the whole number of phase encoding steps and then redistributed them to individual echo trains. And this way, adjacent points in K-space are sampled at close echo times, and this way you get a smooth K-space filter along the echo train. So the sampling proceeds like that, so not one average after the other, but you sample like that. And as a next modification, you can basically project back the points to fill the gap between adjacent phase encoding samples. So what you're actually doing is you do a phase encoding oversampling, and if you rearrange the data this way, you just need a single Fourier transform or a Krappa or iterative transform to get your image back. So how about results? I tried that on a low field scanner from Siemens, and I choose acquisition parameters to make sure that I get very noisy data. As you see at the bottom there, you recognize the image, but it's really very noisy. If you do two conventional averages, you get an increase in signal to noise by the expected 40% or so. If you use the same number of acquisition steps, but use the weighted averaging, then you see you get much better signal to noise and also much better image appearance. So this works really very nicely for very noisy data. If your data are not too bad to start with, like here at the top, you could do just conventional averaging and you get already nice images, but nowadays you even do not need any averaging. You can apply some mild noise filter with AI and you get good images. So the message there is weighted averaging really is it for situations where your signal to noise is really very bad. Of course, you can use fancy and advanced AI to retrieve signal even there. There are some papers out for ultra low field, but you have to be aware as soon as your noise gets too strong, then the resulting image will be dominated by whatever information went into the AI filter. So if you use a general AI filter, that gives you images with a lot of what's called hallucinations. If you use MR images, it actually may look nice, but still the image will represent more what is coming from the AI and not much coming from the actual sample data. So my advice there is use weighted averaging to get the best signal to noise you get, and then you can, on top of that, you can improve using noise filtering. So the take-home message is there. Implementation has been done as phase encoding oversampling. You can reconstruct using compressed sensing and whatever is your favorite reconstruction algorithm. And this phase encoding oversampling is actually good even with in a regular scenario. So if you take these weighting factors like shown here, 1 and 20%, then you can reconstruct an oversampling in the phase encoding direction with a simple Krappa reconstruction. And the use case really is very low signal-to-noise scans like chemical shift imaging, ultra-low-field MRI, and especially imaging of heteronuclei. Something like that also feasible in the readout direction. Well, you cannot translate that one-to-one. It wouldn't give you anything to leave out samples in the readout direction, but what you still can do an uneven sampling in the readout direction by reading out data not under constant readout gradient like you normally do, but using, for example, such a wedge-shaped readout gradient where then at the center of your acquisition window, which will then also be the center of K-space, you have a lower gradient, meaning you have a lower bandwidth, meaning you have a higher signal-to-noise around the center of K-space. If you do just a simple Fourier transform on this data, then the images will look very strange. They will basically be compressed and also get some artifacts. But if you do a non-uniform Fourier transform, you get the image information back, but just as with weighted average in the phase encoding direction, you will also get some blurring. So factor of 0.2, 0.4 is something which is feasible and gives you about 30% improvement in signal-to-noise for the same acquisition. So again, this is something to be considered for things like sodium imaging and so on. I don't have a specific use case for which I did the implementation. Probably one can also do better than using this triangular-shaped readout gradient to improve image appearance. Okay, so let's go on. My presentation seems to be frozen.
Maybe give it a little bit of time.
Okay, now it's there. So the next variation I want to briefly present is also something which I have published a long time ago, which is to just put a longer echo time at the beginning of the signal readout. The initial hope for that was that this way one would get back the nice contrast for iron-containing nuclei. But as you see in the images, the image appearance doesn't change very much, which on one hand is good. On one hand, you may ask why do that? Well, it gets interesting if you do something during that first echo interval, and the something which I like to do is to put in diffusion gradients. And this is something Andreas Holl from Maxim's group has already been using to get diffusion-weighted imaging of the muscle. So you see it's a single-shot implementation, and you see you get a nice diffusion-weighted image. I wouldn't try it on the head. Well, I did try it, and I got, as expected, quite horrible artifacts because the brain is pulsating, the ESF is pulsating. So it's not something which is suitable for brain, but for whatever structures there are which do not have intrinsic motion. That's a nice option to really do nice diffusion-weighted imaging, and it maintains the advantages of the TSE. You don't have any deformation to deal with, so it gives you quite nice results. So for the next implementation, which is one where I have been putting up quite some work recently, I made use of the fact that signal behavior in a multi-echo train changes very much if you change the phase of the respective pulses. So if you go from CPMG condition, where the excitation pulse is orthogonal to the phase of the refocusing pulses, you get this nice coherent superposition of all the different refocusing pathways and very nice signal amplitude irrespective of the actual flip angle of the refocusing pulse. If you make all the pulses, excitation pulse and refocusing pulse with the same phase, then the signal decays very, very fast because you get a destructive interference of the various refocusing pathways, and you see also independent basically of the flip angle, so independent of the B1 field, the signal goes away very fast. Note the first echo, of course, is identical. At the first echo, the spins don't know yet whether they will undergo a CP or a CPMG sequence. How can that be used? Well, it can be used by shifting the excitation pulse by a duration which leads to a 90-degree phase evolution of a FET signal. Then FET signal will actually see a CP sequence, whereas water sees the usual CPMG sequence, and actually the effect is quite drastic. So this is the usual implementation with the CPMG mode, and if you just change by 0.7 milliseconds the time of the excitation pulse, the images start to look very much different, and you see all the FET signal go away. You also see that in this space above the nasal sinuses, also because of the local field inhomogeneity, you also lose some signal. If I look at the evolution of the FET signal as a function of this DTE, one sees that the minimum occurs at around 0.7 milliseconds. If you take the 420 hertz difference, it should be actually more like 0.6, but one has to keep in mind that FET is not a single line, it has multiple lines, so experimentally something between 0.7 and 0.8 that gives you a minimum signal. Here on top, that is with a conventional FET set pulse, and that is also represented by this red line, and you see the performance is more or less the same. I wouldn't make too much about that. It's actually the FET suppression seems to be a little bit better in this CP implementation. So this is basically a very cheap way to get FET suppression. You don't need any additional FET suppression pulse. You just make this one change and automatically your sequence is FET suppressed. The downside of that is that, of course, this is then also quite sensitive to B0 inhomogeneity. So I made some attempts on the body, but I didn't get really good results because the suppression profile, which basically is represented by that curve here, is not ultimately sharp. So you really need good B0 homogeneity. So the use case for which this may be useful is for high field imaging, where you may have problems with B1 inhomogeneity. I actually had some problems on one of the last sessions I did at a 7 Tesla scanner, where I couldn't get a good FET suppression because of the B1 inhomogeneity of the RF core use. So I already tried that at 5 Tesla, and it works very nice. That at United Imaging, and yeah, I would like to try it at 7 Tesla or even higher. So in scenarios where you really have problems with B1 homogeneity, but not with B0 homogeneity. So final modification I'd like to talk about a little bit is interleaved acquisition mode. So if you run your protocols, typically you run one protocol after the other. In an interleaved mode, you jump between two protocols, so you interleave per TR. And this basically gives you the advantage that you have basically identical sampling conditions for both protocols. The implementation is done, in a very basic way. So you will find in the repository this TS plus ileaf, which is just initializes the sequence, and then you run through this Pulseq loop. So you can then use this Pulseq modality, which I introduced at the beginning, to define whatever you want to change between the scans. You can, of course, do more than two scans. The implementation is quite basic. I didn't attempt to make that elegant. I made it more practically useful. It's computationally rather wasteful because for every TR, the whole sequence is calculated again and again, but the computation is fast, so this doesn't matter. On the plus side, in order to use that for whatever implementation you are working on, you just need to add or remove some comments in the sequence, and the sequence, basic sequences are marked like that, so you can very quickly get that done. And of course, you can interleave TSE plus with TSE fast, and actually you can prepare any other sequence. You can throw in gradient echo or whatever you like. It's basically, I mean, the most straightforward application is if you do modifications of parameters which do not affect the basic timing structure, like different echo times, flip angle schemes, diffusion weighting, whatever. If you change the TR, or if you change the number of slices, you need to put in additional modifications to maintain a constant TR between individual slices. So basically, you could interleave your whole examination protocol, but that's not recommended for once the resulting sequence gets very large. So this may cause problems during sequence loading. Also, too long overall acquisition times will lead to intrascan motion and degradation of overall image quality. Just an example, and that was more coincidental example. I didn't mean it to be an illustrating example, but it turned out to be. So when I run through some modifications of this shifted excitation pulse, I made a successive scan, and one sees that yes, the difference clearly shows the fat, and the brain signal is the same, but you also see that between scans there was some slight motion of the volunteer, which I think is very typical. Volunteers keep very quiet during the scan, but when the scan is over, they relax, and that relaxation can lead to displacement. So in the same session, I also run an interleaved acquisition, and now you see whatever motion happened during the scan affects both images the same, and so the difference is very clean and really shows the fat signal only. Okay, so that the quick run through some of the modification I've been made. You find everything on GitHub. I took a long time to really write a manual which explains everything, because that's something I always complain about when people put in their code on GitHub, but do not give any manual, any idea on how to use the code. So this manual really explains in detail all the different functionalities. And basically, I call the sequence TSE plus, but if you're living not in the Siemens world, I also made versions of the product of the manual with FSE plus and Rare plus. You can guess which one is my favorite, and the manuals are, apart from this nomenclature, identical. I didn't provide renamed sequences. You have to do that by yourself if you like. So with that, I'm on the end, and I thank you for your attention.
Thanks so much. I think that sequence and manual should be like mandatory for anyone doing MR, probably, especially with Pulseq. Any questions? I have a small question, low-level one. I was trying to understand in your diffusion-weighted TSE, the spin echo TSE sequence, where does the motion sensitivity come from? Is it multi-shot or?
Well, if you have macroscopic motion, that means you get the phase of the signal will change, and as you saw in the demonstration of CPMG versus CP, the echo train is very sensitive to motion, so you very easily lose a lot of signal.
I see.
I mean, if you run a brain scan continuously, you will see that about 40% of the scans will show dropouts, and some of the scans will look nice, but yeah, it's not very practical. Also, of course, if one is serious, one can do better than having the simple Sayce-Kaltenner implementations.
I really like the CPMG versus CP trick. That's really clever.
Actually, it came about when I made some mistake, and I, by coincidence, made a different TE for the first excitation pulse. And actually, took me a while to figure out why the images suddenly looked so much different.
That's really cool. So neat story. Oh, we are actually over time. Any last minute question? I don't know if do we want to get into the kind of the latter half? We usually do a little Q&A, but we did a little bit of that already. I don't know.
I think we did most of it. I think everybody's so impressed by Jürgen's presentation that basically you answered all the questions, and I personally find it really impressive that in 40 years, not all is done yet. There's really so much room for creativity there. It's really quite amazing. And yeah, thanks for sharing this all, because it's I think it will give also a lot of food for the thought and food for the next I don't know, master and PhD thesis. A question next to the manual. I know you were also working, or at least considering to work on a paper about all that. Is it something which is also coming?
Yeah, for this shifted excitation, the paper is more or less finished. I did some more scanning last week, and I put that in. So I hope to get it published as a note in MRM. And this modification, TSE plus versus TSE fast, will be the next one I try to make a paper of.
Cool.
So I have to admit, when I retired, I initially thought I will never write a paper again, because the review process, submission process is such a nightmare. I don't want to waste my lifetime on that, but yeah, I tried anyway.
Okay. I think we can call it a day. I see a few people already had to leave, so I assume.
So yeah.
Good times. Okay. Probably a good time to end.
So thank you, Jürgen. Thanks everybody for participating, and looking forward to many more papers to cite this work. Right.
Okay.
Great.
See you around.
Bye-bye, everyone.
Bye bye.